In this video, we are going to find all possible values of n such that 1, 1, 1, 1, 1 at base n is a perfect square. Before we move on, don't forget to give a like, subscribe to my channel, and turn on post notifications. To solve this problem, I'm going to write this equation in an algebraic form. For the left side, I'm going to write in expanded form, which is starting from the leftmost digit is 1 times n to the power 4. Next is n cubed. Then we have n squared, n, and finally 1 equal to some integer squared, say m squared. Then at this point, I'm going to multiply some constants on both sides, preferably a square. Recalling that if we have something like this, n squared plus n plus 1, I'm just going to take a case with a smaller degree. And the complete squared, we actually multiply by 4, or we do it like this. Take out a quarter, 4n squared plus 4n plus 4, and then these two terms will be part of an square of a linear expression with integral coefficients. So then, inspired by this, I'm going to multiply both sides by 4 again. So we have 4n to the power 4, 4n cubed, 4n squared, 4n, and 4 equals 4m or 4m squared, or we can say it's 2m all squared. And then I'm going to try to write left hand side as some like very close to some perfect square. I know it's not a perfect square of any quadratic expression, but let's try to make it as close as possible. So imagine we have some unknown times n squared plus some unknown times n plus some unknown, all squared. We'll make this close to the left expression as possible. So let's say ABC. If I expand this square, then I'll have a squared times n to the power 4. For n cubed, the coefficient is 2ab. And then for the square term, we have 2ac and b squared, multiplying b and b, and a times c, or reversing the order. N squared, while for coefficient of n is 2bc. And at last, we have c squared. So looking at this, it's intuitive to take a equals 2. A equals 2. So then for this, we have 4. For 2ab equals 4, then we should take b equals 1. So then this equals 4 again. Now from this, we have 4c plus 1 times n squared. So it seems unlikely to reach 4n squared at this point. So either I take, if c equals 0, then we have n squared for this term. This term equals n squared, or if c equals 1, then this term is equal to 5n squared. Or if we go further, c equals 2, then this term equals 9n squared. Now let's move on and see what else we can do. Now for 2bc, it becomes 2c. And c squared, we still have no information about it yet. So it seems that if c is taken, if I take c to be some value that is larger than 2, then clearly we will have all square terms, the linear term, and constant term to be larger than 4. I mean the coefficient is larger than 4. If we take 0, then all those terms will have a smaller coefficient. So then from this we can say that observe that for all n, well, false positive, for base we do not take negative values, we will have 2n squared plus n all squared is less than our given quartic expression. Let me mark that down. This squared is 4n cubed plus 4n to the power 4 plus 4n cubed plus n squared. And this quartic, our given quartic, must be less than 2n squared plus n plus 2 all squared. And this squared is actually 4n to the power 4, 4n cubed, and then 9n squared plus 4n plus 4. So we know that no matter what n do we take, this value must be less than, I would say it must be between 2n squared plus n all squared and 2n squared plus n plus 2 all squared. And if we want this quartic to also be a square, then it must be somewhere in between. And it seems that because we are working on positive integers, they are discrete. This tells us that our quartic, if it has to be a squared, it must be equal to 2n squared plus n plus 1 all squared. Now if C, this actually refers to the case when C equals 1. So we've actually done quite a lot of expansion already. This is actually 4n to the power 4 plus 4n cubed plus 5n squared plus 2n plus 1. And the first two terms are cancelled out, so it seems it's just a very simple quadratic equation at this point. It's n squared minus 2n minus 3 equals 0. So we just factorize and solve. Of course, we won't have base minus 1, so it's base 3. Now let's see whether the 5 ones in base 3 is really a perfect square. So checking. So starting from 3 to the power 4 plus 3 cubed plus 3 squared plus 3 plus 1 equals 81 plus 27 plus 9 plus 3 plus 1 is 121, and it's really a squared. So it's valid, and this 3 is the answer we want. Please feel free to share your ideas in the comments. Thank you for watching. See you next time.